Hello, this video introduces our work on leveraging episodic memory to improve world models for reinforcement learning for the NeurIPS workshop MemARI. This research project was undertaken jointly by UCL and Huawei Neuromorphic Lab. On this slide, we're going to expose the rationale for this project. Episodic memory has been proposed as a solution to the sample inefficiency of deep-RL, which has been coined as Episodic-RL. However, Episodic-RL has been mostly concerned with episodic control, where given a state and an action, you output a value estimate. Interestingly, cognitive neuroscience research suggests that episodic memory is also used in the process of modeling the environment's dynamics. This could also make sense in deep-RL, with world models being parameterized by artificial neural networks. Indeed, the non-parametric benefits of episodic memory mappings could also assist better transition dynamics estimates at low experience. This is because deep learning suffers from low learning rates to avoid, for instance, catastrophic forgetting, and therefore can only incorporate experience at a very slow rate. So we propose the Episodic Memory Module for world models, EMWM in short. This slide summarizes our project where we leverage episodic memory mappings, but here instead of standard episodic control, our episodic memory predicts the next latent state given our current one and the action undertaken. We combine it to the famous RSSM world model used for the Dreamer v2 agent. And we test it on 6 different Atari games. These are some of the preliminary results we obtained. These plots represent the evaluation return on the y-axis and the number of steps on the x-axis. Interested by sample efficiency, we focused only on the 2.5 first million steps. The blue and green curves show our models with the change of 1 hyperparameter. And red is without, so standard Dreamer v2 essentially. We can see that our agent seems to offer more sample efficiency for 3 of the 6 games, namely Hero, Montezuma, Revenge, and River Raid, which is quite interesting because those are very sparse reward environments. It is worth noting that these results were retrieved without extensive hyperparameter tuning of the model, which we'll detail more in the next slide. Here we explain how is EMWM implemented, which is only a proof of concept for now and relies on heuristics from cognitive neuroscience. For prediction, the X-spread most uncertain mappings are replaced by EMWM, where uncertainty is measured using deep ensemble disagreements, shown in the following equation. In terms of storage, the X-store most surprising observations are stored. Surprise is captured by the KL divergence between the prior prediction of the next latent state transition and the posterior of that prediction given the observation, denoted KL obs. Finally, for deletion and update of the episodic memory, we got inspired from forgetting curves, and we associate each memory to a recall probability, R equals the exponential of the time times x decay, divided by the KL obs. Inspired by memory consolidation, we also rebump R to 1 whenever a memory is used for prediction. Thanks for listening. You can drop an email for any question, tips, or recommendation.